Pleasure to announce our next speaker, Professor Vafadar, with a talk on divergence-free form-bounded type drifts. You are welcome. You have 25 minutes for talk and 5 minutes for questions.
Okay, thank you so much. First, I want to thank you to the organizer that let me and give me this opportunity to attend at this great conference. This is a joint work with Damir Zembelatov. He's my advisor, associated professor at University of Laval. We are working on divergence-free form-bounded type drifts. Throughout this study, we investigate the classical regularity theory for this elliptic equation on RD, where the dimension is greater or equal to 3, and the coefficient, the matrix A, it's measurable uniformly elliptic matrix, and also the drift term B, it has low regularity, and it's divergence-free as well. What motivated us to study this elliptic equation is that because it's a good proxy to this parabolic equation, and this parabolic equation plays a central role in hydrodynamics. And also, this parabolic equation is behind the following SDE, this passive tracer SDE. And as you know, when we are in dimension 3, the vector field B is obtained by solving a 3D Navier-Stokes equation, which is highly singular, and also it is divergence-free. So far, there has been several mathematicians who has been studied the regularity theory when they have highly singular drifts. One of those vector fields which cover a large amount of highly singular vector fields is BMO -1. The vector fields in this space are presented as the gradient of some skew-symmetric matrix with entries in BMO space, which means that, as you can see in the footnote, their BMO norm is finite. There has been several mathematicians who work on this vector field, like Zhikov, Sergin, Silvestre, Chevrag, Zolotos, Kianji, Hara, and many others. And they established a pretty strong result on a priori and a posteriori Holder continuity of solutions for both elliptic and parabolic case, and also they established Gaussian heat kernel bounds as well. Just to give you more example, for example, the LD class or the large component Tomore class, both of these classes belongs to the BMO -1 vector fields. Also, another vector field which cover the large amount of singular drift is form-bounded vector field. The drift in this vector fields are in L2 locally, and also they satisfy this F delta condition for all phi in the Sobolev space. Indeed, this condition enables us to control the control the B gradient. Here it enables us to control. It enables us to control this term B gradient with respect to minus gradient A gradient. Yes. And to give you an example, again, LD space or large component Tomore classes belongs to this vector fields, and there has been several results, good, strong results by great mathematicians like Kinzembelatov, Semenov, Zhang, Hara, and many others. They established gradient estimate, solvability of SDEs, a priori and a posteriori Holder continuity of solutions for the both elliptic and parabolic case. And the next vector fields which cover the strong singular drifts is the multiplicative form-bounded drift. These vector fields contain the drifts are locally integrable, and also they satisfy this multiplicative form-bounded condition. The same as the form-bounded vector field, it enables us to control B gradient with respect to minus gradient, A gradient again. As an example, this multiplicative form-bounded vector field, it contains the weakly form-bounded vector field, F delta to the power 1/2. And in the footnote, you can see the definition of the weakly form-bounded vector fields. They are locally integrable, and they satisfy this quadratic type inequality for all F in the Bessel space. And I would like to note that we can show that we can show by interpolation inequality that form-bounded vector fields are strictly inside the weakly form-bounded vector fields. Also, there are some results when the drift term belongs to the multiplicative form-bounded drift. Kinzen-Belatov and Semenov, they proved a priori upper and lower Gaussian bond when the drift term belongs to these vector fields. In the both cases, when B to show the regularity theory, it is more common to use the DiGiorgi method. And also, when the drift term belongs to the BMO -1, or when the drift term belongs to the F delta, DiGiorgi method plays a key role to show the regularity theorem. And the first step to show to run the DiGiorgi method is to prove the Cauchy-Pauli inequality, or you might be more familiar with the energy inequality with weights. So to have the DiGiorgi method, when you have different kind of singular drift, you will have different approaches. For example, when B belongs to the F delta space, to show the Cauchy-Pauli inequality, we first use the quadratic inequality. And also when we are in BMO -1, to run the DiGiorgi method, to have the Cauchy-Pauli inequality, we use the divergence theorem and also the John Nirenberg inequality. In this work, when we are dealing with multiplicative vector field, we are not able to use the quadratic inequality. It doesn't give us, it gives us nothing. So we come up with a certain iteration procedure in order to have Cauchy-Pauli inequality and be able to run the DiGiorgi method to another third class, which means MF delta class of the singular divergence-free drifts that contains F delta, and also it is different from BMO -1. We use the same iteration procedure to run Moser's method as well. The statement of our results, we consider this elliptic equation when the matrix A is uniformly elliptic, which means that it satisfies the following condition. Also, we consider that B belongs to the drift and belongs to MF delta, which you are already familiar with. Just to give you more comparison between MF delta and F delta. In MF delta, our drifts belongs to L1 locally, while when we have F delta, the drift term are twice, they should be twice integrable. And also the MF delta is different from BMO -1. During in our paper, we allow B to have more physical application. We allow B to have a singular divergence, which means that we allow that the divergence of B, the positive part and the negative part, belongs to F delta. To give you more history about the MF delta space, this class was first introduced by Semenov in the context of Nash method as a condition to guarantee the a priori two-sided Gaussian bonds. He obtained a priori Gaussian upper bound with Moser's method and a priori Gaussian lower bound via a deep modification of Nash method. Indeed, he introduced some G functions in order to, he proved the Gaussian lower bounds. And it was one of his remarkable achievements of Semenov. Here, I would like to put more emphasis that he proved a priori, not a posteriori via energy method. Here is our theorem. As you know, I already mentioned the assumption on the coefficient. Here, we show that the Dirichlet problem, when the solution is equal to some bounded function and it's with finite Sobolev norm, it has a weak solution which is unique among all weak solutions obtained via approximation method. Also, it satisfies the gradient estimate over the balls inside omega for some generic constant C and for some generic P greater than 2. And also if the function G is positive, then we proved a posteriori Harnack inequality via the Georgi method for the supremum bound and via the Moser's iteration for the infimum bound. To prove the Cacciopoli inequality, like the old school method, we multiplied the equation by U eta, where eta is the cutoff function, and it is equal to 1 on the smaller centric ball, and it has the following properties. The gradient of eta satisfies this property, and then we integrate by part. We obtain the following main inequality to have the Cacciopoli inequality. As you can see, if we had no drift term, then we simply had the regularity on the left-hand side. So the goal here is to control the red term. So as I already told you, if the drift term belongs to the form-bounded vector field, if F delta, we can use, as you see, we can use the quadratic inequality, and then we apply the F delta condition on this term, and then we simply have the Cacciopoli inequality for the main inequality. And also when B belongs to the BMO -1, we are able to, we apply the divergence theorem here, and then we can control this term by the John Nirenberg inequality, and then again we have the simply we have the Cacciopoli inequality. As you see here, we have yes. In our case, when B belongs to the drift, when the drift term belongs to MF delta, and let's say the divergence of BB0, then we come up with this upper bound. Just we are applying the condition of MF delta, the condition of MF delta, and then we come up with this upper bound for the red term. As you see here on the right-hand side, we have U on the larger ball, we have U on the larger ball, U on the larger ball, but here the gradient on the larger ball. As you remember, on our main inequality, we have the gradient of U on the smaller ball. So this makes a problem for us. This is a troublesome term. So to deal with this problem, indeed, this problem leads us to run a new iteration method. Indeed, if we put this upper bound on in our original inequality, and then we are able to run some iteration between the smaller radius and the larger radius. And then this leads to Cauchy-Paul inequality for us. Also, we use the same iteration method to run the Moser's method, to run the Moser's method, but with a slightly more sophisticated form. And also, I would like to give you just a small flavor of this iteration. For, if you are familiar with the Moser's method, we multiply the equation by u to the power -1 eta, right? And then we apply the we do the integration by part and apply the properties of the cutoff function and its gradient, and then we come up with an inequality, right? If we introduce xm, the sequence xm, as follow, where w is the logarithm of u. If you are familiar with the Moser's method, this is what we come up in the when we multiply the equation by u to the power -1 eta 2, then we are able to rewrite the equation in terms of logarithm of u, or indeed in terms of w, and then this is a natural definition for xm. And then we can rewrite the equation in terms of xm. Then the inequality will be rewritten as follows. So we are able to iterate this inequality, and then we will find an upper bound for each term of this sequence as follows. So what we are interested is for the first member of this sequence, which means that for m equal to 1. So we will be able to have an upper bound for the gradient of w, which is the first step to run the Moser's method. Also, I'm going to note that we are working right now on the second project, and we are now investigating on the regularity of the solution to the parabolic equation. And our goal is to develop the regularity theory for this corresponding parabolic partial differential equation when the drift term belongs to MF delta, but in the parabolic frame, which means that the drift term it satisfies this condition where G here, GT, is an integrable function, and delta is finite. Thank you for your attention.
Thank you for your very nice talk. You actually finished much earlier than the schedule provides, so we have plenty of time for questions.
Oh. Okay, I'm ready.
Please, questions? No questions. Okay, then I have a question. Okay. My standard question on that conference. From your personal point of view, which of the results presented is the most important?
I think Harnack inequality. If right now we prove the the supremum bound for the parabolic equation, and we are working on the infimum bound, and if we prove the Harnack inequality, it guarantees that the SDE, which is correspond to this parabolic equation, it has I think it has a generator. I'm not really familiar with the SDE part, but I know that I know that Damir, he's more expert in that area. But I know that if we prove the Harnack inequality for the parabolic case, then we can be sure that the SD has the generator or something like that. But I'm not sure. It's
Okay.
about Markov process, and which is not my specialty.
Okay, thank you. More questions? Please, questions? So it looks like there is no questions. So let us thank the speaker again.
Thank you.
And we are finishing this talk.